Okay, next up we have Niamh Mimnagh from Maynooth University with her talk, Predicting Outbreaks of BVD on a Herd Level for Irish Cattle Herds.
Okay, hi everybody. My name is Niamh. I'm a researcher based in Maynooth University in Ireland. And for the last few years, I've been working on using machine learning methods to predict BVD emergence in Irish cattle herds. So, normally I give this talk to pure statisticians who don't know anything about sort of ecology or epidemiology or anything. So I normally start off by explaining what BVD is. It's probably not necessary at all in this room, but I will do it anyway. BVD is an economically important infectious disease that affects the dairy and the beef industries. It can cause a range of health conditions, including infertility, fetal abnormalities, and miscarriage if an animal is infected while they are pregnant. If they're infected within the first 120 days of gestation, they'll produce a calf that's what's called persistently infected. And for these persistently infected animals, there is no treatment, there is no recovery. They will be infected and spreading the disease for as long as they live, which is normally not a very long time. Animals that are born with this kind of untreatable gastric issue don't tend to survive very long. Prior to the implementation of an eradication program in Ireland, it is estimated that BVD cost Irish farmers about €102 million every year. The eradication program was implemented in 2013, and it has four main components. So the first one is removing these persistently infected animals from the herds. The second is monitoring for and treating BVD infections when they arise. A really important one is vaccinating all of the animals of like breeding age, and an increase in biosecurity measures. So that refers to being more aware of your imports and your exports and how the disease can cross boundary lines. This eradication program has proven really successful in reducing BVD in Ireland. It is, however, a little bit expensive. The first 5 years of the program cost about €54 million to run, and I assume the subsequent 7 years have been something similar. So the aim of this project was to see if we could find machine learning methods that could predict BVD well enough that they could be used in conjunction with this eradication program to make, I guess, educated calls on whether animals in a certain herd needed to be vaccinated in a given year, or whether they might be safe to go without. Like I said, the eradication program has proven really successful. In 2013, 11.3% of Irish herds were BVD positive. So they experienced at least one case of BVD in that year. By 2023, this had dropped to 0.42%. And this is obviously a really good thing for Ireland in its goal for BVD freedom. For me, what this means is that the data that I'm working with is really imbalanced. There's a huge number of negative herds, and there's very, very few positive herds that I'm dealing with. And this data imbalance is something I need to take into account when I'm using my machine learning methods. Because there's a load of machine learning methods that could be used with this kind of classification task. Not all of them are going to be effective with imbalanced data. So what we needed to do first was to set up a little test to see which machine learning methods would do well with imbalanced data. So to do that, we simulated data so that we could test it. This is the setup of our simulation study. I'm not going to go into details of the statistics of it or anything, other than to say, first we simulated data where we had 50-50 negative and positive herds. And this is sort of the ideal case from the point of view of a lot of machine learning methods, this is what they deal with best. And from there, we reduced and reduced the number of positive herds in our data sets. So we looked at 50-50, and then we looked at a situation where we had 90% negative herds, and then 95%, and then finally 99% negative herds, which is similar to what our real data looks like. To simulate the data, we first had to simulate all of our covariates. And we wanted to simulate covariates that were similar to the covariates that we have for our real data. We have a huge amount of data on the herd sizes, so we have the number of dairy animals, the number of beef animals, the number of animals of varying ages. We have movement data, so the number of animals that were moved to different farms and to different marts and to the abattoir and things like that. We have imports and exports. We also know the previous year's disease status, so whether the herd was negative or positive the previous year. We simulated all of our covariates. We combined them to make a risk score of sorts for each herd. And the final step in our simulation was to assign positive or negative to each herd depending on their risk score. So for our 50-50 split, the herds with the highest risk score, the 50%, the top ones, were classed as positive, whereas when we were looking at 99% negative, only the top 1% in terms of their risk score was classified as positive. So once we had simulated our data, we wanted to test all of our machine learning methods. The machine learning methods that we looked at, we sort of grouped broadly into two families. They're the multiple class classifiers and the one class classifiers. They're also called anomaly detectors. The multiple class classifiers, what they do is they train using all of your data, so your negative herds and your positive herds. And that includes commonly used ML methods like the random forest, support vector machines, and XGBoost. The one class classifiers are less commonly used, I think. And for the most part, the way that these work is they are trained using only the negative herds. So they don't see the positive herds at all during training. And the idea is that they would learn the negative herds so well that they would be able to pick out the positive herds as being different, as being anomalies. This includes things like autoencoders, isolation forests, the Mahalanobis distance, things like that. When it came to measuring the predictive performance of our models, we also needed to take the data imbalance into account. You can't look at something like the accuracy when you've got really imbalanced data, because if you had a model that just predicted that every herd was negative for BVD, and we've got 99% negative herds, then you'd have a model with 99% accuracy, but it would be completely useless for predicting BVD. So with that in mind, we were looking at the recall and the precision. In our case, particularly the recall is what we're interested in. What we want to do is to really prioritize correctly predicting the positive cases. The recall and the precision, they take imbalance into account because they take into account the number of negative and positive predictions that you have, both correct and incorrect. The methods that I have on the screen are only a small number of the ones that we looked at. When I was putting together this presentation, I was wondering if I should go into any detail about the methods. If I was to talk about all of them, we'd be here all day. So in the end, I decided I would just not explain any of them, and if you're interested, you can ask later. I was going to explain isolation forests because they were the best out of our one-class classifiers in the simulation study. When we went to use them on the real data, they didn't work at all. So I'm just going to skip that one. So this is the results of our simulation study. The ones that are grayed out didn't do very well. So the ones that did well were the random forest, the lasso model, the elastic net, XGBoost, and of the one-class classifiers, just the isolation forests. So we took the models that worked well in our simulation study, and then we used only those on the real data. And these are the initial results that we got for our model implementation on the real data. So we have our 4 multi-class classifiers and then our isolation forest. For the multi-class classifiers, we looked at fixing the data imbalance using resampling and comparing it with the raw imbalance data. And for random forest and XGBoost, we looked at weighted classification. And these are the best recall values that we got for each of them. So, like I said, the isolation forest did not do well at all. The best one that we have here is the random forest with a recall of 0.876. And what that means is that it's correctly predicting 87.6% of our positive herds as being positive. Looking at our random forest more in depth, in this table, the middle line is the results that we just looked at, the 0.876 recall. So for that one, it is correctly predicting that 219 out of 250 positive cases are positive. It is also incorrectly predicting just under 47,000 negative herds as being positive. And you might look at this and think, oh, well, that's no good. It is sort of a characteristic of this type of really imbalanced data is that you're going to have an issue with false positive predictions. But from our point of view, this actually isn't that bad because the current approach for the eradication program is that they are currently testing and vaccinating all herds. So if you were to go with this sort of approach, you would be correctly picking up on those 219. You're incorrectly picking up on about 47,000, but that still represents a 50% decrease in the number of unnecessary vaccinations and tests compared to the current approach, which is just blanket testing and vaccinating everyone. If you wanted to improve the number of positive cases that you get, you can sort of play with your machine learning method a little bit, sort of tweak the classification threshold. So on this bottom line, we've reduced the classification threshold, and we're getting more of those positive herds. But we've also massively increased the number of false positives that we're getting. So what we wanted to do from here was to see if we could play around with our results to improve the number of positive predictions we have while avoiding this unnecessary increase of about, 30,000 false positives. So to do this, we started looking at ensemble learning. And ensemble learning is a catch-all term for a couple of different methods that take individual machine learning methods and put them together to improve their predictive performance. The one that we've had the best luck with is method stacking. And the way that this works is we train all of our models the way that we did before. And then we get another model called a meta-algorithm. And we train that using the predictions of our other models. So on this table, the bottom line is the best results from the random forest by itself. And on the top line, we have the results of our method stacking approach. There is a typo in this where it says 240, it should be 230. So sorry about that. But using the method stacking does increase the number of true positive predictions while keeping the number of false positive predictions fairly static. There's a slight, ever so slight increase, I think 22 hertz out of 93,000 is really nothing. So as a summary, using these ensemble methods has led to an increase in true positive predictions, and a very, very slight increase in false positive predictions. And like I said, the current BVD eradication program approach is to test and vaccinate every herd, which can be an expensive, time-intensive and resource-intensive task. By using these machine learning methods to predict herd-level BVD, we are currently managing to decrease the number of herds tested by 50%, while still correctly identifying 92% of the positive herds as being positive. I'll finish up by acknowledging that this work is funded by the Irish Department of Agriculture. Thank you. Any questions for me? I don't have an agricultural background, so if they're veterinary, the answer is probably I don't know.
That's good because it's not a very agricultural question. So it's fine. So you mentioned that your isolation force? Is that right? Yeah, isolation force performed reasonably well in simulation, but then
yes.
not in real data. So I imagine you thought a bunch about like why that might be and sort of what in your data generation process caused that to happen for some methods, but not for others. I'm really curious. What are your thoughts?
I think that I think there's two things. I think maybe our data generation process wasn't complicated enough. Mm-hmm. We tried to take into account nonlinear interactions with covariates and things like that. We weren't just sort of creating linear effects, but possibly there were complications in the real data that just aren't taken into account by the simulation study. I also think that with the one-class classifiers, what they're trying to do is to pick out the positive herds as being significantly different from the negative herds. And that might just not be the case. It sort of, when it comes to the covariates, it's not the case that all of the really massive herds have problems with BVD, whereas the small ones don't. Or say there could be herds that are importing a load of animals but don't have any BVD problems, whereas you know. So I think it's just possible that these kind of methods are assuming that it's easy to differentiate between negative and positive herds, and I very, very possibly that's not the case.
Thank you.
Thank you.
Hi there. So I actually have a question as well. I've seen that you achieved a very good accuracy at the end. Now, when you are trying to communicate these results to both experts and non-experts, how they are considering your results? Did they trust them?
Yes. So in my communication, I work with policymakers in the Department of Agriculture. I also talk to people with a veterinary background and farmers. And the consensus has been that they are happy with these kind of results. The main thing that we were sort of worried about was the issue with the false positive predictions, and it was them who told us that actually, no, that's kind of fine. It still represents possibly quite a significant savings in terms of resources and time and money to incorrectly test and vaccinate 50% of the herds.
Thank you.
Thank you.
Hello, so I'm Anna, and I have a question about your variables. So you said you have many variables. Have you also done studies of which variables are the most relevant and some variable selection to get more insight what maybe should be measured or what...
The most relevant ones.
Yes, exactly. What's relevant and what's worth gathering or what's worth including in the models to make them maybe more faster or you know, optimize them in that regard?
Yes. Yeah, we have looked at variable importance for each of our models. By and large, the most important thing is obviously whether the herd was positive in the previous year. That's almost always the most important variable in terms of predicting BVD. And we've used models like Lasso, which does select the most important variables. So in those ways, we are sort of trying to avoid using unnecessary variables. Other than whether the herd was positive in the previous year, whether the neighboring herds were positive in the previous year is, of course, the second most important thing. I think normally the third place is something to do with animal deaths. Generally, whether the number of animals that were stillborn is also very important.
Okay, thank you. And do you also check how these models with various variables influence the false positives?
No, we haven't actually gone really deep into comparing the false positives of the different models, or how different numbers of variables would affect that. That is something to look at.
Yeah, or like some variables might be maybe more prone to
Increasing the number of, yeah, no, we actually haven't looked that deep into that, but that is definitely something to look at.
Thank you.
Thank you.
Darren Shaw, University of Edinburgh. I was wondering if you've looked at the 20 farms that you are missing in terms of, do they look a bit different to the other 50,000 in some sense?
Yeah, we tried. So far, we've come up with nothing really for that. We've been trying to see sort of what differences there are, or if we classify on a local level rather than on a national level in terms of the classification threshold and things like that. Would that pick up on these extra ones? So far, the answer is no. Yeah.
Any other questions?
Thank you.